Okay, so thanks so much for having me here today. I'm going to talk about asymmetric taxation, pass-through, and market competition, providing evidence from rest sharing and taxes. For some reason, okay. So when deciding whether to tax a product, policymakers need to consider the effect on price and output. For this reason, the study of tax pass-through and its welfare consequences has received considerable attention in economics. While the existing literature focuses on taxes imposing the same amount on all products in the market, in practice, some taxes are asymmetric, meaning that products competing in the same industry may be taxed in different ways, or even only a subset of the product may be affected by the tax. Example of this kind of policies situations are found in environmental taxation, but even in the digital industry, where special taxes on big tech platforms like Google or Facebook are on the policy agenda. Since equilibrium responses to symmetric taxes can affect the relative prices of products and services competing in the same market, asymmetric tax can have a very large effect on competition and market outcomes. In this project, I'm going to study what are the pass-through rates and the effects on market outcome of an asymmetric tax schedule. The context of the study is going to be that of a congestion tax levied exclusively on rest sharing, but not on traditional taxes. This is relevant. The special context of the study allows me to make two additional contributions. The first one regards the policy debate regarding the regulation of online peer-to-peer platform competing against traditional incumbents in regulated industry. This is not only the case for rest sharing competing against taxis, but also, for example, for the competition between traditional hotel and Airbnb. In addition, I'm going to I'm going to study the pass-through of in a two-sided market, which is an understudied area. So let me start by talking about why tax pass-through in online two-sided markets may generate additional insights. So let's consider an example of the rest sharing market where the initial equilibrium is at point A, at price PA, average price PA, and number of pickups, number of equilibrium number of rides QA. A tax levied on riders would shift demand inwards, moving the equilibrium to point B. Here, there is a pass-through rate below 1, and there is a lower price earned by driver and a lower number of equilibrium trips. This would be the final equilibrium in a traditional one-sided market. However, at this new equilibrium, the earnings of ride-sharing drivers are lower, which implies that their willingness to work for the platform goes down, and this in turn shifts the supply inwards, moving the final equilibrium to point C. This simple example shows how tax pass-through in a two-sided environment may be very different from the one of a one-sided environment, and it is possible also to rationalize tax overshifting and so pass-through rate above 1. Obviously, the attacks on ride sharing would also have an impact on the equilibrium in the market for taxi rides. Intuitively, if the degree of substitutability between the two services is large enough, we would see a shift in the demand for a taxi. Here, I'm assuming that prices are regulated, so we will see an increase in the equilibrium number of taxi trips. So I'm going to study all these aspect using the policy variation provided by the congestion tax implemented in Chicago. Chicago is the third largest market for the taxi and ride sharing industry in the US, and it's a city in which the usage of ride sharing grew significantly in the last years. This growth, according to a policy report issued by the city, was also the main responsible for the increase in congestion. Therefore, starting January 6, 2020, the city replaced a flat tax of 72 cents per ride per each ride-sharing trip with a more complex schedule that depends on the type of the ride, whether it is downtown or non-downtown, where a downtown ride is defined based on the endpoints of the ride. And depending on whether the ride-sharing trip is single or shared. You can see that the tax was pretty large, and it was up to $3 per ride for downtown single rides. This basically is currently the largest tax on ride-sharing implemented in the US. So in a nutshell, what I'm going to do in this paper is first estimating the effect on trip prices and compute tax pass-through rate. Then, given the change in price, I'm going to look at the number of the change in the number of ride sharing and tax equilibrium pickups, and this is going to tell something about the substitutability between traditional cabs and ride sharing. Then, given that the policy was nominally motivated by a desire to reduce congestion, I'm also going to explore whether the policy was effective in this dimension. And finally, I'm going to develop a simple logic framework to quantify the welfare effect of the tax. So let me jump into the data. I use data from the City of Chicago data portal, which include two main data sets on taxi trips and ride-sharing trips. Ride-sharing are also called transportation network providers, so TNPs. These two data sets include any kind of information at the trip level. The only issue is that for the ride-sharing data, I do not observe a driver identifier, and I cannot tell the company which supplied the ride. I supplement these data using information on weather in Chicago from the National Weather Service Forecast Office. This plot gives you an idea of the kind of variation that I'm going to use it and the kind of variation that I have in the data. In particular, like it's the top two lines show how there was a change as compared to the year before the tax is implemented in the average price of a downtown trip. So this kind of ride saw an increase of $3 per ride, and you can see that in fact the final price paid by rider was much higher after the tax. Okay. In order, since the policy was implemented in January 2020, and after a couple of months, the lockdown for COVID-19 started, I can only identify the short-run effect of this tax. So to do so, I use a regression discontinuity in time design. So I use time as the running variable. However, if I were to use a traditional RD design, there would be a concern due to seasonality, since the congestion tax was implemented in the first Monday after our long peak period of holiday, in which naturally every year I saw that the price tends to increase. And even in the graph that I showed you before, there was a price increase at the policy cutoff in the previous year. So to address this concern, I implement a different design which I label differences in regression discontinuity, in which I pull together two subsamples, one including 29 days on either side of the actual policy date, and the other including 29 days on either side of an hypothetical policy date, which is the first Monday after the holidays in the previous year, which was January 7, 2019. In this way, the intuition is that I can subtract the post-holiday effect and isolate the effect of the congestion tax. So this is the baseline specification that I'm going to run. I'm going to consider different dependent variables from the prices to the equilibrium number of pickups to the average speed of taxis, which I use as a proxy for congestion. The main variable, the main coefficient of interest is in this specification is beta, which capture the additional effect of the congestion tax on top of whatever is implied by seasonal variation in the first Monday after the holiday. I ran several robustness check. First, I considered different bandwidths. So I mentioned that I constructed the two subsample using 29 days. For robustness, I'm gonna use different subsample longer, so up to 34 days, and shorter, up to 24 days. I'm gonna use Poisson regression for count variables. And I also check whether the results are robust using a more traditional difference in different design, which uses variation of the tax schedule across different areas of the city. In the interest of time, I'm not going to talk about this robustness check, but all the results that I'm going to show are robust to these checks. So let me jump into the results, and here you can see that the top part of the panel shows the effect of the congestion tax on the price of per trip. For almost all the type of ride, there was a significant and large increase in price, meaning that the platform passed through the increase of the tax more than completely for some time from some types of ride. For example, for single rides, I find that the pass-through was above 100%, which is consistent with the example that I discussed at the beginning of the talk. There are also other factors that might explain in this setting a pass-through above unity. For example, the fact that ride-sharing companies are multi-product firm, and so an increase if they increase the price on single rides, for example, part of the demand is gonna switch to share rides, and this obviously provides an extra incentive for them to raise prices. I also look at the change in the equilibrium number of pickups, which are consistent with the change in price. So after the congestion tax, there was a significant reduction in the usage of ride sharing. Furthermore, I look at the effect on taxi pickups, and I find that there was an increase, as conjectured at the beginning, in the number of equilibrium pickups completed by taxi driver. However, all these increase is driven by an higher number of pickups in the downtown area, which is consistent with previous literature showing that taxis and ride sharing compete in a more intense way in the densest area of the city. And this is due to the matching the street tailing technology of taxis, and which push them to look for rides in areas in which the demands is denser, for example, the downtown area of Chicago. I then look at the effect on congestion, and I find that the congestion did not decrease after the tax. While this may seem surprising, it's in practice consistent with the increase in taxi trip and in the reduction in the number of the ride sharing shared rides that are pulled together. So after the tax, the number of users that was ride are pulled together goes down. So basically, the number of vehicles driving in the street of Chicago did not decrease after the tax, and this can explain why there was no effect, no significant reduction in congestion. This result is also robust to to specification which focus on specific hours of the day, like rush hour, or to specific geographic areas like downtown. So in the last part of the paper, I also develop a simple logic framework to quantify the welfare effect of the policy. I set up a model with two markets, one for downtown rides and one for non-downtown rides. And I consider three services: taxi, shared ride sharing, and single ride sharing. I also allow for an outside option, which can be taught as for example, public transit. The utility of a rider choosing to ride with product J in market T is defined in a traditional fashion, where C, J, T represent the inherent quality of the product, and alpha is the utility of price. Assuming that epsilon is a logit error, I can compute the market share and study the effect of a final change in the tax on market share. Given this, I can compute these formulas, which only depend on pass-through, which estimated in the reduced form framework, and I can match these theoretical moments with empirical estimates to calibrate the model. Once I calibrate the model, I can study the welfare effects of the congestion tax and also consider some counterfactual policies. For example, in C1, the first counterfactual, I consider what would have happened if the taxi drivers were to charge as a single ride sharing. Overall, I just want to mention that the congestion tax had a large negative effect on rider surplus and total welfare. On the producer side, there was a reallocation of share of producer surplus from ride sharing platform to traditional taxis. So let me wrap up since I'm running out of time. I studied the effect of a congestion tax levied exclusively on ride sharing trip. I find that the pass-through rate was above unity for single rides, and this can be explained by the two-sidedness of the market, but also by the fact that ride-sharing companies are multi-product firms. I find that the tax shift demand back to taxis in downtown, but where competition is more intense. And even if it was normally motivated by desire to reduce congestion, the tax was ineffective in this dimension. Finally, the tax significantly reduced rider surplus and reallocated the share of producer surplus from ride-sharing companies to traditional taxis.